All right, so I'm going to kick off today's demo with a little bit of a refresher as to where we left off last time, and sort of leading into the final culmination of our state channel API, why it's cool, why it matters, and how it's going to work for those who develop with us. So beforehand, we talked about the different components in our existing Node 2.0. So as for those who are more familiar, there are two protocols occurring at any given time on a full Constellation node. So a Constellation node has, in a full node, has two separate processes that handle different components of the wider HTTP network. So the most famous one that we talk about a lot is the L0 protocol. This is what allows different L1 protocols like Bitcoin, Ethereum, whatever, to transact and basically convert value between ledgers in a completely decentralized way without any centralized exchange, interacting in between. So, we can talk about this a little bit more, but this is our concurrent consensus that runs on a full node. And we also have the L1, which is the DAG component, really, of what's going on here. So this is our L1 protocol, similar to like how, a Bitcoin or Ethereum or whatever actually process blocks and transactions, as opposed to come to global state convergence. And so when we look at, if you ever looked at the DAG data, you'll take a look at, a node inside of our directed acyclic graph of, the actual state of the network. So these different nodes inside of that graph are created by the L1 protocol, and the edges as well are used in creating those nodes, which then stitch the graph together. So that's just sort of a high level as to what's going on and what's up with Node 2.0. So last time we talked a little bit more about the specifics of what's going on under the hood. I'm going to just sort of gloss over that now because we're going to take a look at the L1 at the end of the second part of this demo to talk about how that corresponds to what LTX is going to look like from the implementation of like the back end or like just the data focused services. So I'm just going to jump to the final conclusion of the last time, which is we have this amazing thing that we've implemented called the arrow. And so an arrow is really cool because it is something that defines a category. What does a category really mean? I mean, somebody can go take a look at this really esoteric math website called NCAT and just lose their shit. But in essence, it's really just a different way of understanding spaces and data that exist inside of those spaces. So in essence, when you went to college and you learned about calculus and stuff, you're pretty much just using geometry in order to come up with some kind of a concrete quantifiable value for something, whether it be a physical quantity, whether it be a probability. And so this extends it into an abstract space that can operate directly on data structures defined by, with any kind of ridiculous kind of topology that we can think of. So what's really important here is that by defining this arrow, it allows for any different L1 to connect with any other L1 by the L0 here. So this arrow essentially creates some type of a type hierarchy or an inheritance or like a lineage inside of the data that is created such that it all extends from the L0. So that's a TLDR as to why it matters. We use this in data validation. And so this is sort of one sort of half of the state channel API that is functional. And so it is really like what's happening under the hood to get the full pipeline that is Node 2.0 ready. So if I'm going to run this starting example, I have a bunch of different nodes that are mocked HTTP servers on my local computer. So this can be easily extended to just run over our live network. And so they're all going to send over a stream a bunch of randomly created transactions. And so over time, we're going to see blocks getting created and then also snapshots. So I just printed out the snapshot here, but the block is just a part of this whole data structure. So it's basically empty, which is totally fine. In essence, what we're creating here are different stateful representations of the network that's running locally. So we're piping transactions in through the L1 that gets sent up to the L0, and the L0 creates these snapshots. Great. So that's like the full kit and caboodle. So what I wanted to talk about today, which is the second half of our state channel API, is something that's really important to how we're going to be developing distributed applications in the future as we kill off smart contracts. So the whole sort of kit and caboodle as to why people give a fuck about smart contracts is that it provided something like a structured query language or some kind of a domain-specific language like SQL, a structured query language, for accessing the resources of computers in an open decentralized network, which is quintessentially like the most like insecure operation one can ever do. In information security, The number one thing that you learn is to never run or even deserialize data that you don't know about on your own server. So it's pretty fucking unbelievable that we got this thing working for many different reasons. But for those who understand what I'm talking about, you can thank me later. So the TLDR here is that, as we showed before, different protocols can be stacked together with some sort of stateful transition, or rather a discrete quantized step that defines a pipeline through which we can just stream data, and all of the processes necessary in order to create the data dependency graph occur in parallel. And so that is really how we're able to achieve horizontal scalability and be CPU bound. So this is why we're going to run on phones, yada, yada, servers, etc. Anybody who doesn't actually follow something that can be scaled up and CPU bound the way that we have will never scale, which is why proof of work is fucked, proof of stake is fucked. And for those who've never heard me talk about it before, unless you're rolling some kind of a new concurrent consensus, you're pretty much just, your old news pumping, a shitcoin. So what's really important here is that we were able to define a monoid, which is in essence the ability for data defined within a universe to be added or for the product of that data to be calculated. So what does that actually mean in an abstract sense? When Bitcoin is operating on data types, all they really give a fuck about are numeric values like 1, 2, 3, or 4. When ETH wants to operate on its opcodes, it really only cares about maybe like a handful of data types that the EVM can actually process. And so we're really left without the ability to referentially verify stateful information across our networks. Essentially, the idea of L2 systems with centralized, servers being some kind of a solution to the Oracle problem, being the only potential solution. So as we know for a fact, that's not true, especially looking at Chainlink and what they've been able to create with the EVM. It's functionally impossible to solve the Oracle problem without concurrent consensus. And without concurrent consensus is not possible without the ability without concurrent consensus, and also the ability to chain information that has different geometries and topologies around it that tell us about different sequences of events that happened in various different orderings. Okay, that doesn't make any fucking sense. TLDR, time doesn't actually exist. It's just a made-up construct for people to understand phenomenons of events, because things only occur typically in a very sequential order at our sort of magnitude in the universe. In actuality, when we're solving problems in dynamical systems, we're constantly thinking about things happening at multiple different times. In quantum mechanics, when you're trying to do something in like chaos theory, fundamentally, like we know this is what the universe really looks like, but we try to dumb it down because we simply can't really figure out, solve these problems with how we're able to compute things today. So in order to understand things that don't occur within some sort of linearity of events, we have to create some kind of referential verification. So this is how in quantum mechanics, we use something called error correction codes in order to maintain quantum states that allow us to know different components of the system, at least up to some sort of margin of probability. And that's all we really know. In dynamical systems, this allows us to understand steady state criteria such that some kind of a system can either, maintain itself and continue generating on, or it's going to die and fall off. And so what we were able to do is take all the really like hard shit about, creating referential data types that allow us to create a linearity across, parallel processes just by creating a plus operation. So right now we're still going to get the syntactic sugar to work, but it doesn't really matter. It's just some random implicit bug. I don't really give a fuck. Bottom line here is that we have this method implemented called combine, which allows us to take two different concurrent processes, just like we showed you before, and then add them together as though they were literally just numbers. Okay, so like hold on to that for a second. Every single other protocol trying to solve cross-chain liquidity is just adding numbers together. This is using that same level of abstraction and complexity to add complex data types. Okay, that's a soundbite for you. So instead of just adding numbers and swapping it back and forth between liquidity pools, we can literally mix ledgers together into a geometric representation of the physical world. Full stop. And so all of that is done just using this addition method. So basically everything we talked about before about defining your own protocol, all these different things, combining with an arrow, that's the hard thing that you need to do to basically create something for a domain specific protocol. That's probably something you'll have to pay Constellation an arm and fucking leg to actually implement for you, unless we find a reason to do that ourselves. Or you can hop in and do it yourself. That'd be wonderful. And if you want to, please send me an email. But in actuality, for the ordinary developer, we really just want to use pre-packaged interfaces for certain functionalities and then mix and match them together. This is kind of like why it's way easier to create a digital circuit than an analog. It's sort of an analogous reference. But the TLDR here is this. If we wanted to extend this into how LTX works, we can basically take our example of this L1 consensus process and make a couple of modifications in order to just create a completely new state channel that is totally linked with everybody else and runs with the same guarantees of this prepackaged interface. So what's really cool here is that I can take, for instance, this L1 cell or even another cell that I want to define and just add these things together. And implicitly under the hood, as long as we follow the interfaces, they will essentially combine themselves together into a streaming pipeline. So basically, without having to understand anything about the actual system components of your service, without having to understand anything about configuration, anything, you can basically create some type of an instance of a state channel inside of a REPL and compile it in the same way that we can use like the Spark shell in order to run real-time queries by creating these objects on the fly. So it's really cool, and I just want to, basically the real magic here is that I can show that by taking this existing protocol and this one and just doing a plus operator, I can basically create a data type that is equivalent to constructing it all the way from the ground up. So basically what that means is if you want to create your own custom state channel, such as in the L1 consensus, we're going to go here and make a modification to the data type to create something that inherits from your omega. That's step number one. So we're going to call this A, and it's going to inherit from omega. You don't actually change this data type, but you just pass this into your instance of a cell. Step two, we'd actually want to make a modification to, and if we actually wanted to make a modification for LTX to handle some type of a cross-chain swap, then we would make a modification to the algebra of a cell itself. So we'll go here inside of the L1 cell. We should take a look at it. Where's the L1 algebra? There we go. Yeah, or sorry, the co-algebra. So in essence, what we're going to do whenever we receive a request to try and do a cross-chain swap is we will create a new case statement inside of this match, this pattern match, partial function block of code, which operates on our special data type A that we just showed. And it basically says, hey, if I get LTX and I want to do a swap, or like what we call an emission transaction, it's going to initiate just a request to the Ethereum network to basically get a valid block that something has been switched on their network. And then the cell is just going to wait for that response and then continue on for the next steps. So those are pretty much the only two areas that we really need to modify the existing pipeline in order to create your own custom L1 based off the one that we have right now. And so that's what's kind of magical about this. And also what's really cool is that we'll be able to combine multiple different L1s, maybe even something like an L2, centralized service onto this by just using the combine method, like A plus B plus C. So you can basically chain these things together without really understanding too much under the hood. Just the same way you can think about, if I have a collection of shit, I should be able to add them together. And that basically just creates the different components of some type of a microservice. So yeah, that was kind of a bit of a ramble. But so as you guys can see, that's the last step here. We have an L1 block in our snapshot that was created just by adding those two things together without explicitly defining the full pipeline that we have over here. So this is the higher level API that's going to allow a lot of individuals who don't necessarily need to understand what's going on under the hood to just build functional products. Thank you.
That was great, Wyatt. Can you that was awesome, man. Could you describe how the token works in this situation?
Yeah, so the token is really just like a data type that gets sent to any kind of ledger. So that's, I guess, fed into our cell right here within something called the co-algebra. This is what creates a cell or like an instance of computation in our network. And so basically, depending on what data you care about, a Bitcoin transaction or something else, you make a request inside of here as the first step to initiate across to whatever other L1 protocol you want to talk to. And then you get the response and you just continue on. So yeah, that's like where like ledgers modify each other. This is sort of where that like kind of bridging thing happens.
Got it. Thank you.
Yeah, absolutely. Also, I will say for people too, real talk, like, when I do, we do implement the cross chain bridge, it's just, maybe it's a demo in itself to just show how long it takes for each to finish, because the whole thing here will take less than a second to finish an entire state convergence, depending on how we configure and create the cluster. So it's pretty much going to do most of its time just waiting for ETH to converge. So it's basically just a wrap process that moves stuff to a new liquidity pool based upon what's been supplied on the L0 side. Yeah.
Got it.
So it's cool. Yeah. So all your different data types, just add a case statement. That's it. We'll probably find something cleaner to do later using our own domain specific language like Solidity. But for right now, we can essentially just use these kind of combinatorial objects to just create these structures. And so as we create more complex stuff, we'll actually be able to visualize what we can right now, but it just looks like a linked list. One of these different monoidally created, data pipelines. And what they do, which is really cool, is they create these kind of dendrite-like structures where each different depth inside of the tree is a different layer inside of a hypergraph or a hypersurface. And every single thing on a hypersurface is a concurrent event. And so there's a flow from top to bottom and back and forth, which is defined by the hylomorphism in those algebras. And this monoid allows for people to not really need to know the global state of HTTP just to get access to what they need. So you can just run a query, be give me this table plus this table. It's basically the same thing for creating servers that serve up data and verify their service. Done.
That's awesome. So when you say complex stuff, more complex stuff, what are use cases that you have in mind?
Well, I mean, the most important thing is basically information that represents the physical world. So in the typical crypto world, we're just creating arbitrary objects of crap that only exist inside of a small universe. Where I guess in the smart contract case, it's what can be defined by the EVM. So in this case, if I wanted to create real world sensor data, if I wanted to create something from a car, if I wanted to create something from, some kind of an IoT device, I can literally use that data representing the physical object in that physical region of the world to make decisions and update the state of the network. Is physically impossible and never will be possible on any smart contract platform due to the fact that they can't handle rich data types. And rich data types allow for us to create linearity to time out of concurrent events. Rich data types meaning they have some kind of a topological order that is represented by this. So everything inheriting from L0, you could, for instance, have another one of these running at the same time. And so essentially, that's a totally valid pipeline. There you go. You just keep adding them together. I mean, I need to add an implicit here for the compiler to be happy, but yeah. Did that make any sense?
Yeah, that's awesome.
Yeah, just slap it on, dude. So anytime somebody wants to take, I've got a sensor network, I got a bunch of drones, I got a fleet of cars. What if I want to integrate all of this information in a cryptographically secure way to enable global situational awareness and orchestrate the physical systems themselves by some type of a decentralized protocol that's Sybil proof. You can do that here with just by adding these different processes together.
Wyatt, can I ask something as well?
Yeah, absolutely.
So basically, I'm just trying to digest this like everybody else, I guess, because it's always kind of it's always amazing to hear you talk, but it's also something you have to process it for a while. So I'm just speaking quite intuitively. So the way I'm seeing it's like you're building these. It for me it just feels like you're making these data type Legos in a way, if I understand it correctly. And these Legos can be they relate to each data type. So it could be an Ethereum data type, Bitcoin data type. It could be US Air Force data type. And you can just basically just plug and play these into these pipelines. Is that correct?
Correct. Yeah, absolutely. That's totally correct. And what's really cool about this monoid is that it allows for you to just think about them as Legos, such that the way that you can combine them is defined by these implicit grooves on the outside. So if they fit, they sit. You're done. You don't have to like literally sit there and like calculate, oh, like this is, my serialized data type. I have to set up this server, yada, yada. Like, no, if this follows by this addition rule, if the compiler's happy, then you can stick together these two Legos.
And how easy is it to, because I mean, if the logic to build on this in basically, like you're saying that people don't have to totally understand what's under the hood. So if somebody is building a bridge from Ethereum or from another network, would that be relatively easy in that respect?
Yeah, absolutely. So if we hop back here to our L1 implementation, in the case where someone wants to just copy DAG and create their own data type, basically what they can do is create a new, sequence of events here. This is a thing that needs to happen inside of a sequence of events that makes an API call to the Ethereum network. So they just create a new data type that extends from emission, to use the language of generative economics from the, the light paper that was released. That emission would be taken in, and then it would create an API call to Ethereum. This cell would wait until Ethereum converges, and then it would perform the rest of its shit. So you just create one more statement of like a sequence of events that needs to happen. And also, if you look at the documentation right now, you can take a look at the sequence of events in L1. So as people walk through, they should be able to see, oh, this is where I'd want to make that API call or that API call. It's basically 3 steps that are step-by-step with visuals. And it's like, if you want to gather data before consensus, do it in this one. If you want to verify what was retrieved by consensus, use it at this part. It's basically it.
Thank you.
Cool. That would make some sense. This is like really difficult, I guess, in terms of content, because basically what I'm talking about is the creation of some type of a, like, I don't know. This is just like really math heavy, and why this like would be exciting to someone is that they basically realize or have ever seen before functional implementations of various different servers, and so we can do, and microservices. You can basically find ways to create a way of joining them all together into some one high level thing, and it just makes life super easy for like people who just want to deploy stuff and rinse and reuse stuff. So yeah. I think we'll hit big in the functional programming community to be like, I created a monoid for protocols. So it's kind of cool. But yeah, I hope that made some kind of sense. The TLDR here is basically just that when you create some kind of a process that you want to be governed by consensus, if you want to integrate it with another project or another protocol, you just do my protocol plus the other one. And that's it. That's what we just saw. So it's a lot easier. And for example, like last thing, and I'll just stop talking because I feel like people are zoning out. Basically, when big data became a thing, and that phrase was a thing, everybody was using a tool called Hadoop. And Hadoop was functionally like the same of all of the tools that we have right now. But what made the currently most famous tool that kind of defines the entire big data ecosystem, Spark, really popular was a high-level API that allowed for individuals to not understand what the fuck is going on under the hood. Hadoop is basically like stitching together different processes using an arrow, and Spark is basically using this different combine operator, which can be used in like a real live setting to just query and test stuff. So it's cool.
That's incredible.
Like,
and when is that ready for a theater near you?
It's done. So it's going to be added to the docs page. Anyone can pick this up and start using it. Couple of days, but you can feel free to share this with everybody. The links I've shared on the docs are the same. The demo from before is the same. This is literally just these tests in the unit tests in the repo that the docs are associated to. So it should be fairly straightforward. If you can just download the code, you can run through anything and start fucking around with it yourself today. It's on GitHub.
Amazing. I think now we need to figure out the features for Lattice so that we can work with all that. That's pretty amazing. Nice job, man.
Yeah, exactly. Thank you. So just to remember those statements right there in the consensus, you tell me what you want Lattice to do, and we'll put steps inside the co-algebra, and then there she goes. There she goes. We'll check each step, and then we'll look at the final data type, and then she's done. So yeah, you let me know.
I love it. Thanks, man. Great job. Great demo.
Thanks. Yeah, thanks. I mean, it's a little bit. There's a lot going on under the hood, but it's just great to see it all working out in the data. And yeah, one other thing I'll mention is that this is going to be used for us to validate state channels before we deploy that. So if we add them together or create like a pipeline, and those two values don't add up, like if they don't have the same value, then we know that there is basically a cycle in the DAG, and that the protocol, your state channel will have points of failure. So it'll throw an error, which is great. Probably should have mentioned that too. That's really huge. So basically you get a compile time on the fidelity of your streaming pipeline, which is a cool tool in itself.
Is there documentation on troubleshooting? If it doesn't validate, then do this. Is that something to think about? Is that like a test net of a state channel?
Well, I think it would, it's sort of up to the developer to be able to read the errors that they see. I think that following this example should be good enough to get someone like a Hello World app working. And then as far as anything else is concerned, we use a couple of really, big libraries, like most notably something called FS2 streams. And so if you ran into any issues, like you take a look at an FS2 form, because, if our, compiler doesn't see any problems, then it might be something around the way in which you deployed. But yeah, literally, like someone needs to get in there and try to build something first. So let's celebrate that happening first.
Yeah, that's rad, man. I'm wrapping my head around it, taking some notes. This is really big.
Yeah, it is a really big deal, man. It's a really big deal.
So let's
hey, Wyatt.
state channels.
Yeah.
Yeah, I'm just putting together some questions here. Using kind of Lattice, I guess, as an example to kind of put things into context. So we're using the term L1. We're using the term state channel. The way that you're defining it, are those two different things, or is a state channel an L1, or state channel can be just a microservice, or does a state channel need to have its own consensus? Like trying to figure out how all those pieces kind of fit.
Sure. Yeah. So the blanket term of state channel just represents anything that has an L1 protocol integrated with it. So like if you are able to create like, some kind of integration with L0, excuse me, I misspoke. The reason why we call it a state channel is because it is one channel in the larger spectrum of all state data that is contained within the L0. And so in essence, when we create a state channel, we are creating a sequence of different cells that represent some type of data flow. So we could call these cells L1s or like L2s. Like these are just descriptors to describe what the cells look like. By a state channel, let me just show my screen again. I literally just mean a streaming pipeline. So like it's this right here, where we just have different cells chained together inside of a pipeline. And so if you can form a pipeline, then that's a channel, where like the channel are the different stages in the pipeline.
Yep, got it.
Yeah. And so just to also add some clarity, a cell is just like a future. It's just like a future with a callback. It's just typed. So there's no like unit or void or nulls.
When we're talking about integrating with an existing L1 such as ETH or Bitcoin, is it required to set up a state channel to act as that bridge between them?
Well, I think hypothetically it might be possible to write some kind of a centralized service that uses the L0, but just from everything I've been focusing on, in essence, what you want to do is create your own cell and then define, interactions with other L1 protocols inside that cell. So let's say you wanted to create a Bitcoin and an ETH token. You could basically make API calls to like Bitcoin ledger and the ETH ledger, and then make updates, and then take the results of that, and then move on. So it's really just, up to the developer.
I see. So it would act like a relay plus resolver type of service?
Yeah, basically. So you can basically wrap up all those types of things into a cell, which is, like I said, a feature. But what's cool about that is that all the different steps inside of the cell are create that represent the data flowing through the network. So the output of your cell is a data structure that represents every single step backed by crypto hash functions. So that's kind of the thing.
Awesome, man.
Yeah.
Yeah,
yeah, she's cool. So I will say for everybody, this is we're probably gonna. Oh, thanks. I appreciate it, man. It's great to have this fucker done. This is basically like that first paper I wrote, but like in real life. This is basically like a server-side implementation of all this, the code I wrote for generative economics too. So yeah, it's live. I will also say just for everybody that the protocol team is now focusing on taking this and getting it to work over network. So the next probably month will be a little bit silent, but the next big milestone will be after that, and that will be all of this stuff working over a live network.
Wyatt, I want to say congrats. This is really amazing, and what I like is the fact how you can abstract these cells and data streams basically to a numerical value and just stitch them together. I mean, that is pretty neat. So yeah. You basically just abstract it to the level of one single number, and you have an entire package underneath that. That's pretty cool. So well done. Thanks.
Thanks, man. Thank you. Yeah, this is really helpful for a lot of reasons, but I think this is going to be the game changer for cross-chain protocols. It's like, how can you create an API that is so simple that it's just setting up, a backend or hosting a microservice yeah. So it's cool. And also just one other thing too is that because we can add together cells of arbitrary computation, like we can create not just a domain-specific language, but a Turing-complete one for distributed systems that's verifiable. So that's also another thing too, which is that we're going to allow Turing-complete programs to be verifiable on our network with Babble. And so by showing that these cells can be added together, it gives a bound that solves the Turing Oracle problem using a nifty little thing called a colored operad. I haven't quite published this yet. It's still an ace up my sleeve. But what this means is that the interpreter for running a verifiable Turing-complete language is tessellation, and it is that. And that works. So that's going to be a huge win for us. You basically write SQL across the internet to have servers do stuff in a verifiable way and have it all be governed and orchestrated by consensus.
Fantastic, man. That's awesome. Yeah. That's huge.
So yeah, a huge dump, lots of nuggets. I know this is probably a lot of fryers. Also, like, I do kind of want to like maybe take not some feedback, but basically like, if people meditate on this, can they just tell me like what nuggets, do they think are good that we should highlight? And I will try to highlight them in our documentation. So just let me know, and yeah, because we're taking a show you in word form now, so that's where we are, and it will be done. Share it to your friends, share it with the world.
Hey, in your mind, like how much effort is it to implement something like Lattice as a state channel?
I mean, like, so basically, like I'm going like as we release like a live like beta of Node 2.0 or like a full testnet before we decide to just figure out how to bring that and all that shit, like I'm going to basically use exactly what LTX is as the walkthrough example for making a custom state channel inside of, the walkthrough. So like once this is done, like the ability to do a cross-chain swap on Rothstein is our milestone for the end of, getting Node 2.0 to work. And then everything after that is just at building functionality with new protocols. So just swapping in one string for another, and then supporting the release of mainnets as marketing and business see fit. Further timelines. So yeah, you'll be able to do cross-chain swaps on Rothstein when I hand this over.
Hi, Wyatt. Nice presentation. I have a similar question going into that direction. So it's regarding state channel adoption or hypergraph adoption. Let's say we have different applications on projects on Ethereum right now, and they see state channels, hypergraph state channels, and think it's interesting. How difficult would it be for them to port their smart contract code over to a DEX state channel?
Well, I mean, in terms of porting their smart contract code over to DAG state channel, like I personally think it'd be way easier to implement a smart contract as just some kind of a service in any JVM language. That's literally all it takes to rewrite it natively using HTTP. Now, if they didn't want to rewrite it natively, they could just copy and paste the cross-chain bridge or ETH or whatnot, make like a lattice clone, and then interact with their existing smart contract using the EVM's, API and the HTTP API. So those are two paths.
The question was relating to the first path. So basically, they want to really move completely over to the hypergraph.
Yeah. So check this out. Well, in terms of how to migrate, I'll be honest with you. Like, I've never migrated a smart contract to a state channel. So, like, whatever headaches people run into or how do you host data and make it decentralized, I really don't know. So I'm just going to say off the top of my head, I'm not going to jump down any product rabbit holes. Like, this stuff is very easy to implement, whatever you can think of, whatever your use cases are. But just to answer from a high level. So take a look right here. This right here is our first demo, right? I showed you, right? This is the arrow. This is a rigidly structured or stitched together state channel without using the monoid. Basically, like, I guess I'll call it the generative API. So like, generative economics, we talk about generative calculus and how do we create generative systems using a higher level, calculus. That is what we showed with the monoid. This right here in the arrows what we showed with blockchain cohomology. But the TLDR here is that if somebody wants to actually create their own custom smart contract, all they have to do is use the scope of their main method to start their service to just initialize, like, I don't know, a hash map. Let's say you wanted to create an ERC20 token on a state channel. I would create ledger equals map of some string to a string. I don't know, maybe I'd call it a numeric or an int. Let's call it a double. And so that's basically it. And then when people want to make stateful updates, they would literally inside of the co-algebra, or it'd actually be inside of the algebra here. Once they get a result, actually no, it wouldn't be algebra, it would be co-algebra. They would make a step in here to basically make an update. Oh, is this a transaction on their network? Then inside of this statement, it would basically be like, make a change to that mutable map and then continue on. So you just take one extra like if-else statement, add it to here. And then inside of these if-else statements, basically that's what this pattern match is. You can access stuff that you've defined inside of the scope of your main method. So like this is how you build like any kind of backend service for like a website. Connecting to a database, hosting just shit that you serve up for the web page. I don't know. I did a lot of backend rather than front end, but yeah, TLDR here is that you just write it as though you would write your own script or an application, and then you add an if-else statement to yourself. Done.
Okay, awesome. Yeah. How is that scripting language called here? What you are using and showing?
Oh, so this right here is all written in like bare bones Scala 3.0 or in Dotty. Was the newest version of Scala. So this is a JVM language. Anybody writing in at least Java should be able to do all of this stuff comparatively. I think you should be able to with the other JVMs. I mean, not think. I mean, you can run them and like have other stuff communicate with them, but like, I just haven't done it. So yeah, Java and Scala for sure work. And so when I was talking about a domain-specific language, or rather our own verifiable programming language that operates on a distributed stack, which we call StackF. Let me share that with you again. This is basically trying to create a general solution to the Turing Oracle problem. The Turing Oracle was Turing's solution to the Turing problem. The Turing Oracle is kind of like the thing people try to figure out. Stephen Spiel proved it possible. This one's a real implementation of it. And so what we want to do is make a modification to use something called StackF. And so what this is a representation of all the different stack space and all the different servers at any given concurrent sort of context of time. Yeah. So that's what we're doing.
Nice. Awesome.
Yeah. So yeah, that's pretty much it. Once we have like our own domain or like our own language, I called it Babble in generative economics in the full white paper, just because it's like, I mean, I actually don't really know the story. Diggle actually told it to me better. I'm not a Christian, or I guess it's Old Testament, whatever. I mean, it's basically like there's some euphemisms there, and it's kind of cool because it allows for the different languages and syntax of different APIs to all have a common language. To basically like self-organize themselves. So it's gonna be cool. I've already proven that, or I created a syntax, or no, what was it? What the fuck is it called? It's my first programming language I ever created, actually. Don't tell anyone. I don't know anybody else who has. So this is basically what's called a, come on. Yeah, language syntax. So yeah, I created a language syntax out of something called category specification language, or categorical specification language. And so this is basically going to allow us to create our own sort of clone of a, I guess you could say a typed ML. What the fuck is it? Yeah, it's a statically typed ML. Right. Haven't read that paper in a few months. Cool. So yeah, that's on page 37 on the white paper on GitHub.
Well, thanks, Wyatt. I appreciate that, man. I appreciate all the time you put into putting the presentation. It's really awesome, man. Congrats.
Thanks, man. Yeah, I mean, it's just a little, some. It's this is how it's all going to work together. So yeah.
I love it. I love it. Well, any parting words?
Not for me, guys. I'm just glad to show you that all this bullshit that I talked about, it seems to be pretty much all together. This is like the capstone of everything I've kind of hypothesized in the last couple of years and everything we're going to be building. So it's just nice to see this actually compiling and working. And so, yeah, everything is downhill from here, man. I mean, this is literally what allowed us to create the day convolution in our, differentiable protocol. So differentiate different channels or layers in a convolution. So have fun, everybody.
All right.
Tell your friend. Go hit the club.
All right, let's dice this up. There's some good nuggets in here. Bye, guys.
Bye-bye.
Bye.
Peace, everybody.
Bye.
Later. A state channel.